How we doing?
Good.
Good. Pardon me. What questions do you have? Things going all right? Well, let's do one more story problem on the same stuff that Hope talked about last time, and then we'll get into some bigger systems of equations. So let's look at this story problem. We've got a gas station selling regular gas for $3.60 a gallon and premium for $4 a gallon. At the end of the day, they sold 185 total gallons of gas for a total amount of $690. How many gallons of gas of each type were sold? So, going along with the suggestion that Hope gave you last time, what should you do first? Yeah, we'll need to set up some equations, but we probably want to identify some variables first, right? Yeah. Did you say that first? I just didn't hear you. That's fine.
No, it's fine.
Yeah.
I said under
All right. So let's set up our variables. What do you want to? How many variables are we going to need here? Two. Good. So I say an x is and a y is. Okay. What should we represent? What should x represent here? Okay, the regular gas, so it's gallons of regular gas in this case. Good. And so the other one should be premium. Good. And notice again, we're saying it's gallons, right? Because the problem's asking you for gallons of each, right? Okay. Now we have two variables that we're trying to solve for here. So we probably want to set up two equations, right? Both of the techniques that Hope talked about last time. Either you had used one equation to solve for one variable and substitute it into the other one, right? Or you use both equations to cancel out a variable, right? Either way, we had two equations to go along with two variables, right? So let's see if we can set up two equations here. What information do you think is going to help us to set up each of those equations? Yep, so what it costs per gallon is probably going to help us out. Good. What else? Yeah, how much was sold and the total sold, right? Okay. Let's start with here. You were told that this gas station sold 185 total gallons of gas, right? What equation can you set up to use that 185 total gallons? Okay. X plus y must be the 185. Good. So notice that again that x and y here are both representing gallons of gas, and it says that you've sold a total of 185. So totaling the gallons, we just need to add them together. Okay, so there's one equation. Pardon me. What about the other? The other equation involves something about a total price, right? So I probably want something equal to 690. What's going to equal 690 in this case? Let me ask you this. If you sell 10 gallons of regular gas, how much money did you make? $36, right? If I sold 20 gallons of premium gas, how much money did you make? 80, right? So how did you figure those numbers out? What did you do? multiplied, right? In the first case, you take 3.6 times 10. The second case, you did 4 times 20. Okay, so now if you sold X gallons of regular gas, how much money did you make off the regular gas? Yeah, 3.6X. If you sell Y gallons of regular or premium gas, how much money do you make? 4Y. Good. And again, we want a total, so we'll add those two together. Now we have our two equations, right? We had two techniques for solving these. We had substitution and elimination. Last time when you did the first story problem, you did substitution. That was the technique that you used. So let's use elimination on this one. Remember, for elimination, you look at one of your variables. Doesn't matter which one, by the way. You look at one of the variables and, pardon me, you look at one of the variables and you try to make the coefficients match, right? Right? Okay. Do you want to make the X coefficients match or the Y coefficients match? The Y's? Sure. What would you need to do to multiply the first equation to make them match? 4. And I'm always going to do, I'm going to multiply it by the opposite so that I can always add my equations to eliminate. We'll see why later. Okay? So if we multiply both sides by -4, you get -4x minus 4y, pardon me, it's a y, equals, gosh, pardon me. What do we get? 760? 440? Oops. Thanks. I mean negative. Good. And then the other equation is 3.6x plus 4y equals 690. And again, now to eliminate the y's, we can just add the two equations together. What do you get when you add? What do you get for the x? The negative 0.4, right? And what do you get when you add your constants on the other side? Negative 50. Good. So then to solve for x, what do we need to do? Divide. So you get x is equal to 125. Now that we figured out x, how are we going to figure out what y is? Yeah, plug it into either of the two equations that we started with. Which one's probably the easier one to plug it into? The first one, right? So if we substitute that into the first equation, you'd have 125 plus, oh my, scrolled the heck out of that. 125 plus y equals 185, so y will be 60. Okay, so we have 125 gallons of regular gas sold and 60 gallons of premium sold. This one okay? I'll leave the last one for practice. It's very, very similar to the one we just did. All right, so let's go on to new stuff. New stuff, but really same stuff. Okay? All right, so what Hope talked about on Monday was systems of equations in two variables. We're just going to bump it up. We're going to do 4 variables. Okay? Now, good news is that for anything that you're ever going to be asked to actually solve, it'll be either 2 equations and 2 unknowns or 3 equations and 3 unknowns. You can keep going, but it's the same process. It just takes longer because you have more variables and more equations. Okay. The process is the same every time. All right. So, when we talk about a linear equation in n variables, what do we mean? Well, remember that you talked about this last time. When you had a linear equation in 2 variables, you had something that looked like that, right? And the reason why you call that a linear equation is because the graph of that is what kind of a thing? A line, right? That's why we call it a linear equation. When we graph it, we get a line, right? Okay. Now, if we're going to extend this, the important part of this is that notice that your x only raised to the first power. The y only raised to the first power, right? We didn't square the x, we didn't cube the y. It's not underneath a radical. It's not up in an e to the x. It's not inside a natural log, right? X is by itself to the first power. Y is by itself to the second power. We didn't multiply the x and y together either, did we? Okay? We did constants, the a and b are just numbers, that's okay, but we're not doing any other function of x or function of y. To extend that to n variables, we do the same thing. We would have some constant times a variable plus some other constant times a second variable plus keep going all the way out to n variables equals some number. Okay? That's what we mean by a linear equation in n variables. Notice again, what's the important part here? Did I square any of the variables? Nope. Did I cube any of the variables? Nope. Did I divide by any variables? Nope. Are any of them under a radical? Nope. Any of them inside of a natural log or up at an exponent? Nope. Okay. When I see a variable, it's to the first power, right? Did I multiply any 2 different variables together? No. Okay. It's by itself to the first power. Okay. That's what makes it a linear equation. Okay. Does that make sense? All right. Now, you talked about in systems of 2 equations and 2 unknowns, you talked last time about the possibilities for the number of solutions, right? What were the 3 possibilities for solutions to systems of equations in 2 variables and 2 unknowns? You had those 3 pictures at the beginning. There's 1 solution or no solutions or infinitely many, right? Remember that the pictures that were on that previous one where you had intersecting lines, right? That was 1 solution. Or you had parallel lines. Those pretend like those are parallel. You had parallel lines. That was no solution. Or both equations that you got gave you the same line, right? They just land on top of each other and you got infinitely many, right? That result, that same idea is true for systems of linear equations in several variables. It's still 1 solution, no solutions, infinitely many solutions. Okay? Those are your 3 possibilities. It doesn't matter how many equations you have and how many unknowns that you have. For systems of linear equations, those are the only 3 possibilities you get. Okay? Basically, if you think about it from graphing, if you needed, say, 2 solutions, your things have to bend, right? If you wanted 2 solutions, do lines bend? No. And that same premise actually works in higher dimensions. Linear equations, if you think about them as graphs, are flat-ish things. They don't bend at all. In order to get more than 1 solution, but not infinitely many, you'd have to bend your graph. Okay. All right. So we can talk about how to solve these things. Our techniques for solving these don't change. We're going to do the same types of techniques in systems of equations that have more than 2 variables, just like what we did for 2 variables. We can use substitution or we can use elimination. Now, hopefully with this example that we're going to do with substitution, you're going to see why we're going to switch over to elimination for all of them. Okay? All right. So remember when you did substitution for two equations with two unknowns, you solved for one of the variables in terms of the other and then substituted in the other equation, right? When you have more equations, when I solve for one variable, I'm going to have to plug it into two equations and then do that process again. Okay, so you get very, very repetitive, all right? So if I want to do this with substitution, if I look at just the first equation here, which variable is probably the easiest to solve for? X, right? Because there's no coefficient there's a coefficient of 1 on the x, right? So if I start with the x minus 3y plus 2z equals 1, I can write that as x equals 3y minus 2z plus 1, right? Add your 3y and subtract the 2z. Okay. Now I need to plug this into the second equation and the third equation. Okay, I got to plug them into both. Okay. So if I plug it into the second equation, I'll have 2 times that 3y minus 2z plus 1. And then we still have a minus y plus 2z equals 0. Plug it into the second equation, or excuse me, the third equation. Take out the x and put in that 3y minus 2z plus 1. We get that equation. Basically what we've done is we've reduced our system of 3 equations and 3 unknowns to a system of 2 equations with 2 unknowns, right? We got rid of we used one of the equations to get rid of one of the variables, right? Okay. Let's simplify this a little bit. We would need it in the first equation, we would need to distribute the 2 through, right? I would get 6y, but then I have a minus y over here, so I would have a 5y. I would have a negative 4z plus 2z, right? If I distribute, because I got to take this times the 3y, that times the 2z. I also have to do it times the 1. Negative 4 plus 2 gives me minus 2z. I have 2. When I take 2 times 1, I'm going to move it to the other side and write it as equal to negative 2 to make it more in that standard form. Let's look at the second equation. Notice there's nothing to distribute in that one, is there? There's just a 1 out in front. 3y plus y gives us 4y. Negative 2z plus, yes. So 2 times 3 is 6, minus the 1. Yep. Okay. And then, where was I? The negative 2z plus the z is a minus z. And then I would subtract the 1 to the other side and get a 5 on the other side. So now I have a system of equations, 2 equations and 2 unknowns. Sorry, I'm trouble spitting it out. I've got 2 equations and 2 unknowns. The problem is telling us to do it with substitution, so let's do substitution again. Looking at both the equations and the variables, which equation and which variable do you think will be the easiest to solve for using which equation? Try to avoid fractions if I can. Keep that in mind. Which equation and which variable would probably be the easiest one to do? Yeah, the z in the second equation, right? Because there's a coefficient of a negative 1, right? That was probably the easier one to do if I want to avoid fractions. You can't always avoid fractions, but if I can avoid the fractions, then it probably helps me a little bit with the arithmetic. So let's look at that second equation. I have 4y minus z equals 5. I could add the z and subtract the 5 and get z is equal to 4y minus 5. Where do I want to plug that into? Do I want to plug it in the first or the second equation? Which equation did I use to find the z? Which one of the equations did we use to find the z? First or second? Second. So I want to take this and plug it into the first. I want to plug it into the other one, right? If I plug it into the same equation, you're going to get 0 equals 0. This is not very helpful in this case. Okay? Plug it into the other equation. We would have 5y minus 2 times 4y minus 5 equals negative 2. I'm going to distribute the negative 2 through. I'll have 5y minus 8y. So I get negative 3y. Negative 2 times negative 5 gives me a positive 10. So we get negative 3y plus 10 equals negative 2. Subtract your 10 and divide by your 3. And you should get to y equals 4. So far, so good? Okay. Is the y value the only one we're looking for? No. Okay. I can use the y value, though, to figure out z, can't I? I can plug it into this one where we solve for z. We'd have 4 times 4 minus 5. 4 times 4 is 16, minus the 5 gives us 11. So we get z is 11. How are we going to figure out what the x is? Where can we plug? What can we do to figure out x? Yeah, use our z and y and plug it in here, right? Plug it into that where we solved for x originally. So we do that, we'll have x equals 3 times 4 minus 2 times 11 plus 1. 12 minus 22 is negative 10 plus 1 is negative 9. When you wrote your solutions for systems of 2 equations, you used ordered pairs, right? We did x comma y, right?
How did you get
12 minus 22. Then I give you negative 10 plus 1. Okay. So when you did your x comma y, you did ordered pairs. In this case, we'll do ordered triples. We'll have an x, a y, and a z. So the x comes first, then the y, and then the z for our solution. Again, this is not really anything new. You did this last time. Hope showed you how to do this last time. We just bumped it up a level, right? The technique's exactly the same, right? It was cumbersome. I think we can all agree that was cumbersome, right? Okay. So let's see if we can come with something that's a little bit more systematic using elimination and coming up with some rules that makes it more systematic. We're going to concentrate this on today and beginning of next week as well. So first, before we get to that point, we're going to talk about what we refer to as triangular systems. Here's why we call it triangular. If you look at what's on the left-hand side of the equal sign, do you see that kind of triangle pattern? Right? So I can see this kind of a triangle pattern here, if you will. That's why we call it triangular systems. Now,
Why do we like triangular systems? Well, notice that, what's this last equation tell us automatically? It tells us the z value, doesn't it? Okay, now what did we do in the original problems? Or, sorry, not the original problems. The one we did last time. Once we found a value, we just started plugging it back into the original ones, didn't we? That's exactly what we can do with this one now, can't we? Which equation should I plug that -2 in first, do you think? The second one, right? Because I can figure out what y is immediately from that, can't I? Okay, so we'll plug this in up here. So you'll have y plus 2 times -2 equals -1. 2 times -2 is -4. Added over, we'll get y is equal to 3. Now that we have z and y, we can plug it into the first equation. We'll have x minus 3 plus a -2 equals -3. We should get x equals 2 when we're done. So then again, if we write our answer, we get 2, 3, -2. Is okay? So wasn't that pretty straightforward to solve? Okay, good. All right. So our goal going forward is going to be to try to convert an arbitrary system, whatever that happens to be that we're trying to solve, into a triangular one. Because once we get a triangular one, the last equation tells us what the third variable has to be. We can go back into the second equation to figure out what the second variable has to be, and then plug both of those back into the first equation to figure out what the third variable has to be. Okay? Hope mentioned this term last time. We call that back substitution, right? We've got a value for one variable, and we work our way back to get the other values for the other variables. That's why it's referred to as back substitution. Okay? So our goal for this particular section is going to be convert the given system into a triangular one, and then use back substitution to get the answers. Okay? That's our goal. All right? So, when we talk about equivalent systems for linear equations, when we talk about a system of two systems of equations are equivalent if they have the same solutions. Okay? That's the whole goal here. We want to change it into equivalent systems. It means we haven't changed any answers, basically is what that means, right? If we have equivalent systems, you should get this, whatever the answer is for one, should be the answer is for the other one. Okay? Now, everything we're going to be doing here are linear systems, so just make sure that we're all on the same page with that. Okay? If they have the same solutions, they're going to be equivalent. All right? Our goal is to figure out a technique for getting a system of equations that were given into triangular form. Okay? Well, there's going to be exactly 3 operations that we can do to do that. Pardon me. Later on, we're going to call these row operations. But for right now, we're just going to talk about the equations with, the operations with equations. First one that you can do is swap 2 equations. I think it's pretty obvious that if all I do is write the equations in a different order, I don't change any solutions. Right? If all I did literally just take equation 1 and equation 2 and write them as equation 2 and then equation 1, I don't change anything really, right? Okay. That's one allowable operation. Another one is multiply one equation by a non-zero constant. That's just what we're saying there is multiply both sides by a number, right? That's all that says. I want to make sure it's not 0, because if I multiply by 0, I may not get an equivalent system. Let me ask you a question. Is that a true or a false statement? That's false. If I multiply both sides by 0, what did I change that into? A true, right? So that's why you don't want to multiply both sides by 0. You might change a false statement into a true one. Okay? That's why I have the word non-zero in there. Okay? Does that make sense? All right. The third one sounds a little weird. Okay? The third one is we're going to multiply one equation by a constant. Add the result to a second equation. And replace the second equation. Okay. All right. That one sounds weird, right? In particular, here's why it sounds weird. We don't actually change the first equation when we do this, okay? We only do it as an intermediate step. Let me explain what I mean, and we'll see more examples of this. Let me go back up to I want to go back to the story problem that we did to start class. Remember when we got rid of the y here? I multiplied this equation by -4 and then we added, right? Why did we multiply by -4 and then add? When I multiplied by -4 and added, it got rid of the y, didn't it? I could have done all of that in one step. That's what the third thing says, right? The third thing says that I could have just looked at this equation and say, do -4 times this and add down and get rid of the y to get that equation, right? Okay. And then notice what we did with that answer. We took that and plugged it back into the original equation without the -4, didn't we? Right? That -4 was really just an intermediate step to help us eliminate. We didn't actually need to keep track of it. Okay? Right? We used it to eliminate, and then I didn't bother using it again because I went back to the original equation. That's what that third operation is saying. All right? It'll make more sense, hopefully, as we do more examples. So let's do that. Let me switch back over here. Okay. Here is our system of equations. It's not written particularly nicely here, so let me just rewrite it so that we can see what's going on. I've got x plus 2y. I'm going to leave a gap for the z. And then I've got a y plus 3z equals 7. And I've got a 2x plus 5z equals 21. The reason why I left the gaps, remember we're trying to make this into a triangular system, right? Does this look like a triangle on the left-hand side? No. Okay. All right, so here's going to be the method we're going to use. And this method that we're going to use goes back to how we had that first example shown to us. Let's go back up. Notice how easy it was, relatively speaking, to solve for each of the variables because I didn't have to divide it by anything at any given time, did I? I had z equals -2. That coefficient was a 1. I've got y plus 2z equals -1. That coefficient was a 1. Same thing here with the x. Okay. This is going to be our method, by the way. We're going to get, in the first equation, we want the coefficient on the x to be a 1. Okay. Then we'll eliminate the other x's. Then we'll do the same thing in the second equation, just with the y, and then the third equation with the z. That's how we're going to work it. Okay. So let's look at the system that we're given. The first thing you want to do is get a 1x in the upper left-hand corner. Do I have a 1x in the upper left-hand corner? Good, that's done. Okay, that was step 1. Step 2, get rid of the other x's. Do I have any x's to get rid of in the second equation? No, but I do in the third, right? Now let's think about it this way. I want to make this a 0. What do I need to add to 2 to make it 0? Negative 2, okay? So this is the operation we're going to use, and this is the notation I'm going to use, okay? I will put a brace here so that we're still talking about systems, okay? I'm going to take negative 2 times equation 1, add it to equation 3, and replace equation 3. That's the notation, okay? E1, E2, E3 refers to equation 1, equation 2, equation 3. Okay? Why did I choose negative 2? Because I want to make the positive 2 go away, right? Notice I'm working off the thing that has a coefficient of 1 here, by the way. Okay? All right, so again, as I said before, this does not change the first equation. It's just used as an intermediate step. Is the second equation changing here? No. So I'm just going to rewrite the second equation. Now let's figure out what the new third equation is. We're going to work down. Negative 2 times x gives me negative 2x, plus 2x gives me 0, right? That went away. Okay? I have to do it everything, right? I'll take negative 2 times 2y gives me what? What is negative 2 times negative 2? Or negative 2 times 2y is negative 4y plus 0 is negative 4y. Negative 2 times 0 is 0 plus 5z is 5z. Negative 2 times negative 1 is positive 2 plus 21 is 23. Okay. So I'm gonna. You don't have to write this in. I'm just gonna point to where these numbers are coming from. This is negative 2 times x plus 2x. Right. This is negative 2 times 2y plus 0. Right. This is negative 2 times 0 plus 5z. This is negative 2 times negative 1 plus 21. Okay. This is why I have it lined up nicely, right? So I can just work on each piece and go down. All right. This was the first step. I wanted to get that nice 1x up here in this upper left-hand corner. Now go to the next equation. I want a nice 1y right here. Do I have a 1y right here? Yeah. Don't have to worry about that. But I want to make this a 0 now to get that triangular form, right? So remember again, I want to see triangle, right? Like that. We agree? Okay. What needs to be added to this to make it go away? 4, right? So what operation are we going to do to make that go away? I want to make this go away using that. What should we do? Yeah, multiply by 4. Good. 4 times equation 2 added to equation 3, replace equation 3. Does that change the first equation at all? No. Does that change the second equation at all? But what equation does it say we're replacing? 3, right? So it doesn't replace equation 2 either. Doesn't change equation 2. What do we get equation for equation 3 now? So remember, I've got to take 4 times everything, right? So I take 4 times the 3z and add it to the 5z. 4 times 3 is 12 plus 5 is 17. So we get 17z here. Now do the other one. 4 times 7, 28 plus 23, 51. Good. Again, you don't have to write this down if you don't want to, but it's just to, again, point out where these numbers came from. This is 4 times 3z plus 5z. This is 4 times 7 plus 23. Questions? Doing it slowly today because we're going to pick up the pace next time. Okay. Is it okay so far? All right. We're got that nice triangle, but really, again, remember we want to try to have those coefficients of 1, right? To get a coefficient of 1 on your z, what would you do with the third equation? Divide by 17. Dividing by 17 is the same thing as multiplying by 1 over 17. That doesn't change the first equation. That doesn't change the second equation. The third equation becomes z equals 3, right? This is that nice triangular form. We've got ones for my coefficient, ones for my coefficient on the x, y, and z, and I see that nice triangle, right? This is what we're gunning for. Okay? So the z is 3. What can I do with that to figure out the y? Good. Plug it back. Yeah, we're going to do that back substitution, right? Take this and go back up 1 step. Y plus 3 times 3 equals 7. 3 times 3 is 9. Subtract your 9, you get y equals -2. And then do another back substitution. X plus 2 times -2 equals -1. So your x is equal to 3. And then again, to finish this off, we'll write our x, y, z as 3, -2, 3 when we're done. X, comma, y, comma, z. X goes first, y goes second, z goes third. What questions do you have? All right, let's do another one. They're so much fun, aren't they? No? Okay, that's fine. All right, let's look at the next one here. Is this triangular? No, okay? Our goal is to put it as triangular. Remember, first step, get a 1x in the upper left-hand corner. That's step 1. Do we have a 1x in the upper left-hand corner? Yes. So I don't have to do anything, okay? Next step, once you get the 1x, make the other x's go away, okay? Let's do them one at a time. What do I need to add to this x to make it go away? -x, right? So what do I need to multiply the first equation by to get rid of that? -1. Very good, okay? So we'll do negative 1 times equation 1 plus equation 2, replace equation 2. Certainly, that doesn't change the third equation at all, does it? We agree that doesn't change the third equation at all? Okay. It also does not change the first equation because the only equation getting replaced is the second one, right? Remember, the multiplication is just an intermediate step. Negative 1 times x is negative x plus x gives you 0. We get negative y minus y gives us negative 2y. Positive 2z, because it's going to flip the sign, isn't it, when we multiply by negative 1? 2z plus 3z gives us 5z. Positive 1 plus 7 is going to give us positive 8. Okay? Remember again, we're taking each of those and multiplying by negative 1 and then adding, right? So you get negative y plus negative y, positive 2z plus 3z, positive 1 plus 7. Not only do we want to get rid of that x, we want to get rid of the 2x. What do we need to add to 2x to get rid of 2x? Negative 2x, right? So how are we going to get negative? What do we need to do then to get rid of that 2x? Negative 2 equation 1 plus equation 3, replace equation 3. The only equation getting changed is the third one. Pardon me. Negative 2 times x is negative 2x plus 2x is 0. Negative 2 times y is negative 2y minus 2y gives us negative 4y. Right? Negative 2 times negative 2z is positive 4z plus 6z gives us 10z. Negative 2 times negative 1 is positive 2 plus 14 gives us 16. Is this okay? Now's the time to ask me a question if it's not okay. Is this okay? Okay. All right, our next step, remember again, got a 1 here, got zeros here, right? Our next step is to do the same thing with a y in the next equation. Get a 1 here. What do I need to do to that to make it a 1? Just divide it by negative 2, right? So we'll do negative 1/2 equation 2, replace equation 2. Doesn't change the first equation. Doesn't change the third equation. It makes the second equation y, I know we got a fraction, minus 5/2 z equals negative 4. Okay, so again, let's think about what we've done so far. Get a 1, get zeros. Get a 1, next step is to get 0, right? What do I need to multiply the second equation by to get that 0 in the y spot in the third equation? 4. Good. We'll do 4 times equation 2 plus equation 3. Replace equation 3. Doesn't change the first equation. Doesn't change the second equation. What happens in the third equation? We did 4 times y minus 4y gives me 0, right? We're trying to get a 0 there. What's 4 times 5 halves? I believe that's 10, isn't it? Negative 10 plus 10 gives me 0. So I get a 0 here. And on the right-hand side, we'll have negative 16 plus 16 gives me 0. That last equation says 0 equals 0. Is that a true statement or a false statement? True. Just like what we talked about last time, this is your indication that you get infinitely many solutions. Okay? So we'll start off class on Monday talking about how to write this. In what we refer to as parametric form. We'll talk about how to write this next time. Okay? And we'll do more examples. But this is going to be the process every time. Okay? Remember, no class Friday because of Good Friday, so I'll see you all on Monday. Okay?